that's really cool. So anyways, hopefully that makes at least as much sense as it's supposed to. And that's why, in order to fit nonlinear problems with neural networks, we need 2 or more hidden layers. And with those 2 hidden layers, that's why we use nonlinear activation functions. Okay, so now coming over to our code, what we're going to do is we'll leave most of this code here, but I'm actually going to, I guess, just comment this out for now. And let's just write a really simple example of this rectified linear function. So I'm going to use the same values from the book. So I'm literally just going to copy 0, 2, -1, 3.3, -2.7, 1.1, 2.2, -100. And confirm -2.7. Looks good. Okay. So then what we're going to say, so those will be the inputs. Now the output is going to just be an empty list to start. And then what we're going to say is for, what do we say, I, in inputs, what we're going to say is if input is, or actually if I is greater than 0, then we're going to output.append I, and then elif I is less than or equal to 0, then output.append 0. And that is the rectified linear activation function. So we can print output, run that, and what we get here is basically everything is clipped from 0 and below to be 0. So I think that's a pretty simple concept. If you're following along in another language, I think you can probably implement something like that. The next thing is, again, still in raw Python, the other option we have is to quite simply output.append the max of either 0 or I, right? And then we can run that, and again, we see we get the exact same thing. So it's just append the maximum of 0 or I. So if I is less than 0, then 0 is the max, right? So pretty simple. Okay, so now what we want to do is actually write the rectified linear object, because we'd like this. Basically what we want to do is we want to have these objects that as time goes on and we build out the code, we need objects that have both a forward method and this backward method for doing forward pass and back pass. So that's why we're going to do this. So for now, this rectified linear object is going to look kind of silly in its simplicity, but soon it will be a little more advanced. So I'm going to copy the name from the book. It's activation underscore ReLU. So class activation underscore ReLU. So the RE is rectified, and then linear unit. And then again here, we're going to define a forward method. It's going to take self and inputs, and it's going to produce a self.output. And we're going to say the output is just np.maximum of the of 0 and inputs. So okay, so that is our the forward method for the activation function that is the rectified linear unit activation function. Now, a couple of people have been asking questions about our naming convention here, and that it's not PEP8. So as a reminder, PEP8 is a styling suggestion, and I know that many people would like to remove that basically and do maybe something like that and so on. The idea here is that we're going to have many different types of layers, and that's just how we're going to organize them. If you really wanted to be official, the way that you would do it is you would have separate directories that would be like your layer directories. So you would, from, you know, whatever package .layers import dense or something like that, right? That's how you would do it. That's how all the major packages are doing it. We're going to try to keep everything simple and in one file. I think it's easier to learn that way. Daniel agrees. So we're going to keep it this way. If you want to change the names, by all means do that. It's really up to you. We're here to teach you neural networks from scratch so that you can do this however the heck you want. That's kind of the beauty. So with that in mind, now that we've got this activation function ready to rumble, we could use it, but the next thing I want to show you guys and that I want us to use is we're going to use the nnfs package. So to get that, you can pip install nnfs, and that will give you the package. Also, as time goes on, especially if you want to use the nnfs tool, which I'm going to explain in a minute, you'll want to upgrade, pip install -- upgrade nnfs so you can get the newer versions of the code. But to show you that, if you just, after you've installed that, you should get the nnfs tool, which you can use to mainly at the moment generate the code files. So for example, if you type nnfs and then code, the part number, and then the file name that you want, this will give you a copy of the code for that part number. So if you want to get the sample code that way, you can. You can also just use the GitHub page and so on. We might add more stuff to this tool later on. Just know it exists. And if you're going to use that, you'll need to upgrade to get the later parts because they're not there. The main thing and the main reason why we're going to use, actually there's two reasons we're going to use this nnfs package. The first is for stuff like NumPy. So our goal and our hope here is that everybody can follow along and get the same values as we do, at least if they want to. Obviously, again, if you're following along in another language, or maybe you want to change things and not do things exactly the same way as I'm doing, which is totally fine, but if you want to confirm that you're doing things correctly, you need to be able to repeat the results that we get. So we're trying to make that possible. So the one thing that we're doing, first of all, the random seed, again, we were setting that so hopefully your random would generate the values that we're getting. But if you're following along, for example, in a notebook, that won't work unless you do that and run all the same code in a cell. So it won't work very well, just as a heads up. But you'll also need to always be doing that. So instead what we're going to do is we're going to import nnfs and then do nnfs.init. And besides setting the random seed, the other thing nnfs init is doing for us is it's setting a default data type for NumPy to use. So for whatever reason, the dot product for NumPy, we only found this out after getting many people in the document and finding some people were getting slightly different values, and it was very weird. But it turns out the dot product sometimes will use a different data type, and there's no way to set a default data type in NumPy. It just decides, I suppose. So instead what we're doing here is we're overriding some things and going to set so everyone uses the same data type. Anyway, if you're in another language, don't worry about it, but if you want to be able to replicate everything, that's how. The next thing that we're going to use the nnfs package for is the data set. Again, if you're following along in another language, I'll either copy and paste this in the description. If I forget to, someone remind me. But anyways, we're going to use this as our data set. And again, this is just a function that will generate some data for us. Eventually, we'll use a real data set, but when we're trying to learn things, it's kind of useful for us to be able to specify exactly what we need of exactly what size, however many classes, however sparse, you can make so many tweaks here and just generate a data set that's either easy or hard and so on. So it just makes a lot of sense at this stage that, one, we don't want to hand type anymore, but also it's just very convenient to use a data set like this that we just create just for learning purposes. So again, if you're in another language, you'll probably need to recreate this in some way, or you can use a different data set. Like, again, it's all up to you guys what you want to do. So this function here is actually slightly modified from the following CS 231 course, which I'll bring up for a moment. And what's cool about this course is it's a heavily truncated version of what we're doing here. I don't think anybody who's following along here, if you're following along and actually don't know how neural networks work, I think you're going to have a really hard time following along here. But instead, what this would be useful for is for review. So as we learn about things, especially when you're done, you might try to come here and use this as a second resource to review, or just see, like, do I understand how they're doing everything here? But anyway, the function that we're using is kind of modified of this, which generates a spiral data set. So I'm going to show you what that looks like. Run that. And what you get is this data set. So you already know it spirals, but if you were told, hey, there's 3 classes here, you might notice, like, hey, maybe that's a class, this is a class, and then maybe this is a class. But then, like, what about, like, in this area? It's a kind of challenging one, especially even here. Like, we know they're all coming from the point of origin, but really I only see 2 spirals coming out of this origin here. So it's already actually a pretty challenging data set, but then when we color it, it becomes a little more obvious. So here's 1 spiral, here's 2 spirals, but as you can see, like, especially green and blue here, they're overlapping quite a bit, like, especially like this here. This is a pretty challenging data set for any machine learning algorithm, but even a human, I think you would find it pretty hard to solve this data set. So anyway, it makes for a pretty good data set for us to practice on. And the idea here of our function is basically you pass how many points basically data set points do you want. So this will be how many feature sets per however many classes you have. So in this case, we're just creating these x and y coordinates basically. So every feature set is only going to have 2 features that describe what class this thing is. And then this is however many classes. So in this case, we created 3 classes. So 3 classes of 100 feature sets each. Each feature set is 2 descriptive features. So just to totally clarify that, that's like our example before was where we were trying to predict server failure, right? And in our feature sets, we had 4 features, and we were saying each feature is like a reading from a sensor. So in this case, we have 3 classifications for something. We've got 100 feature sets, and inside those feature sets, we have 2. So 2 features rather than 4 features. Hopefully that makes sense. Hopefully everybody's following along at that point. But basically, we just have these 2 data points that should be informative in some way of what group or class that thing is. If you're confused, please post questions below. If enough people are confused, we could probably create some sort of animation to depict what's going on there, if necessary. So that's the data set. And if you're using NNFS, you're just going to say from nnfs.datasets, import spiral_data. And then to create the data, where this spiral data function produces both your features and your labels. So we're going to say x, y. So again, capital X just denotes your feature sets in machine learning in general. Lowercase y is like the targets or the classification. So x comma y equals spiral data, and we'll say we're going to have 100 feature sets of 3 classes, and that will be our data. The next thing is we'll just do 1 layer for now, and I guess we'll delete this. And so again, let's delete layer 2 as well. So as a reminder and slight review, so layer dense, this is going to be that first layer from our input data, which is our currently just basically this x. So what was this, right? What was this for? This was the number of inputs, and then 5 was the number of neurons. Now, if you recall from the previous video, you could make that 5 whatever the heck you wanted, right? It could be any number, right? It was the first number here, that's like the input data. What is the size of the input data? So again, what was that 4 talking about? That was the number of features per sample for our whether or not a server is going to fail, right? In this case, like I was saying before, because as you've seen, it creates a graph of XY data, right? So that means we have 2 unique features that describe this data set, right? So in this case, rather than 4, it becomes a 2. So that's our layer 1. And the next thing that we're going to define is our activation function. So we're just going to say activation 1, and that will be activation ReLU. That will just be a ReLU object. So in this case, what we're doing is we're going to have this activation ReLU. As you can see here, this is going to be input. So it's going to take all of the values from our neurons and produce the activation for this entire layer. Now, again, you don't have to actually have the same activation functions in that entire layer. They could be mixed. I can't say I've ever seen anyone do it. And in this case, the way that we've coded things, it's not going to work if you wanted to do that. But again, you should be able to do that if you want. But in this case, it's going to apply this activation function to the entire current output of layer 1. So after we do this layer 1.forward, so we've passed data to, at this point, at layer 1.forward, what we've done is inputs times the weights plus the bias, right? We've done this calculation when we run forward. So now layer 1 has a dot output, right? So what we could say is we could call this, let me make sure I call this the same thing that we do in the book. So yeah, we'll just run, actually I'm not even calling it anything in the book. So we're just going to simply run activation 1, and then we'll run a forward. And then what will we put in here? It's going to be the layer 1 dot output, and that will run everything through. So in fact, let's print layer 1 dot output, just so we can see it right before we run it through the activation function. So in this case, you can see lots of negative values. Okay, there are some positive values, but there's also many negatives. So what we expect to see after we feed it through here, because that's negative values after we've done the weights and the biases, right? So now it's going to go through that rectified linear function, and that should make all of those negatives a 0. Okay, so that's our expectation. Hopefully we'll find that is true. So we do activation 1 forward, layer 1 output, and then now what we can do is print the values from activation 1. So activation 1 output, we'll comment out the other print. Let's go ahead and run that. We typoed. Forward. Save that, run that. And sure enough, what we see is no negative values, many 0 values. And you might think that, oh, that's going to be a problem. Well, when the optimizer goes to start optimizing things, those values are going to get tweaked over time, and we probably will see as training occurs that we won't have as many just purely, 0 worthless values. That's the hope. And again, if we do find that, wow, everything's going to 0, the network is dying, recall that one of the fixes that we could make immediately to solve for this is to initialize biases to some sort of non-zero number, for example. It will unlikely be the case that this is going to be a problem, but now you know. How could we check that? Well, you just print it out, right? Look at it. And that's how you begin to diagnose some of these errors. Anyway, a lot of information for, honestly, basically this. But hopefully you understand now what activation functions are doing and why we use activation functions, and the rectified linear activation function, which sounds kind of complicated, or it sounds complex. It's a cool name, but it's actually unbelievably simple. So anyways, that's it for the rectified linear activation function. In the next tutorial, what we're going to be talking about is the softmax activation function, which is a bit more advanced and really more specific to the output layer, which we kind of hope will be a distribution, but we'll explain that in the next video. Again, if you want to check out the book and get a jump on the material in advance, you can check out the book at nnfs.io, where we are much further beyond the softmax activation function. It's actually training full loop, and hopefully at some point it won't even be a pre-order. The book will be done. At least at the time of my recording this, we're all the way through to fully training a model with optimizing and backpropagation. All of that stuff is already done. So check that out if you want to get a jump on the material or just review it before or after and all that. So anyways, nnfs.io. Questions, comments, concerns, whatever, feel free to leave those below. Otherwise, I will see you guys in the next video.